Welcome. Numbers can be introduced in many different ways. I was introduced to numbers using the Cuisenaire picture, and for me numbers are still associated to color, to shape, to geometry. Here I have a couple of pictures which have been used to represent numbers, maybe historically first. One has used pebbles, stones to count, and that has been then replaced by marks on bones like the Ishango bone. It's a simple arithmetic, but it's also still used, say, when you are playing card games. You're still using these marks to add up numbers. The Cuisenaire picture is very intuitive from the multiplicative point of view. Cuisenaire has thought a great deal also about the psychology of numbers. You see, for example, if you look at 6, and 6 is a dark green, and that's 2 times 3. So there is a relation between that. Or if you look at 4, which is the purple, that's 2 times red. So that's also related. And for example, 10 is 2 times 5. That's also related in the form of color. So we have a lot of different ways to talk about numbers. A computer thinks about the binary code. The Kippus about numbers in the form of knots, which is a very, very geometric topological picture. I once in 2016 thought about numbers as a Morse complex. It actually has been done earlier. I was not aware then by Werner 2011, but it's a very poetic picture and uses the multiplicative structure of the numbers. So for example here this complex represents the number 30. Now what you do is you connect two numbers, previous already introduced number and the new number if divides the other. So 30, if we have introduced 30, we have attach a cell to a one-dimensional complex. So this is a one-dimensional complex we attach to. For example, if we attach 14 and we attached 14, we have put a handle of dimension 1, a one-dimensional ball, to 2 and 7. Here we have attached a two-dimensional ball to this circle. So it's a Morse handle picture, and every time you add something, either you don't change the topology. For example, if you add 4, that's not even represented here. We left it out because it's homotopically not relevant. But if we add a new prime, for example, we add a zero-dimensional handle, and so on. So this is then has an interesting Euler characteristic. Euler characteristic is probably the most important functional in geometry overall, and the Euler characteristic is 1 minus the Mertens function, which is a number theoretical function, minus mu x. Mu x is the Möbius mu. Then this is actually the Poincaré-Hopf index, and if you add it up, that's the Poincaré-Hopf theorem. So I was interested still in 2016 in this Poincaré-Hopf thing. Still interested in that. It's a beautiful picture, and so the Euler characteristic here in this case is equal to 4, because that has Euler characteristic 0. That's homotopic to a circle, right? This is, you can collapse that together. That's a circle, and that's plus 4. So this is the Mertens function of 30 is minus 3. It's a very poetic picture, but it uses the multiplicative structure of the numbers. Now, more recently, in the context of Sar theorem, I got interested again in integer partitions, which is an additive picture. So integer partitions have been represented in many different ways. I used the Cuisenaire picture in high school. This is, I think, historically maybe the first time that such toys have been used for serious research, because I got new theorems using that and using that tool. But I was not aware of this young picture when I showed my finished work to my high school teacher, Roland Sterck. He was telling me about this young tableau. It is an interesting picture also, this Young tableau, and is important in representation theory. Different DNA also is a topological way how numbers or information is stored. So these are molecules, right? Geometric objects. Or here in kindergarten you learn, 1, 2, 3, you learn using this pebble picture. I myself have not learned from that. We didn't use that in school. We use this, and I think this is much better. Yeah, so this is kind of the partition complex which we have seen. You can add partitions, which is the join of the corresponding graphs, and you can also multiply them, which is the strong multiplication of Sabidussi, and that produces a semi-ring, which is dual using the graph complement to the Shannon ring, where the addition is the disjoint union and the multiplication is the Shannon multiplication. So this is a larger algebra. It's number system than we are usually think about. It's more geometric. All the graphs, you can think about the graph as a number, and you can add graphs and you can multiply graphs. So you have an arithmetic. You have actually a semi-ring which you can complete, Grothendieck complete to a ring. Now this Grothendieck completion, say from the natural numbers to the integers is kind of a little bit artificial. It is, of course, you learn that in first or second grade that they are negative numbers, right? When you take 3 minus 5, you get a negative number, and you introduce these negative numbers a little bit artificially. You have to convince really a child first that they are negative numbers. Now, in a context which I want to get into, reflection geometry, Coxeter theory, Coxeter geometry, this is much more natural. And I want also maybe get back to something I learned in college. I had a good geometry teacher. He was a high school teacher also, Max Jäger, and he stressed very much the Spiegelungsgeometry, the geometry of reflections. So if you look at our space here, this is a nice vector space, right? The addition of vectors is additive, and it produces an additive structure, and it's commutative, right? If you take A plus B, that's the same thing than B plus A. It's the same vector. Now you can think about this differently, and that's already Klein and others have thought about, and especially in Germany, Spiegelungsgeometry. What you can do is you don't take the translation as your basic objects, and not the points and space is your basic object, but the reflections at the point are special. So these are the points. The new points are the reflections. And so this is actually kind of a picture you also are familiar with in quantum field theory. When you look at particles, when you have the Pauli principle, if you do something twice, you get back, you have involution. So if I take the reflection at this point, this produces an involution. I take the reflection at this point, this produces another involution. If I combine these two reflections, this plus this, what I get is a translation by taking two reflections. So this is very interesting and kind of gives you kind of like a double space, but it's non-commutative. So what you get is you lose commutativity. You have a non-commutative group. This reflection group is non-commutative. A times B is minus B times A. And that's something we see in particle physics. That's maybe from numbers to particles. So in 2006, I was interested in the question, Kronecker claimed God made the integers, the rest is the work of man, and I really like critical thinking, and that's what we teach. Has been neglected a little bit the last couple of years. We were discouraged to think independently, but critical thinking is very important, and you can challenge everything. You can also challenge the question, is the addition really, which we know from the numbers, is this really the most fundamental thing? If you take 5.3, 5 plus 3, that's 8. Of course, that's the same thing than 3 plus 5. So there's an additive structure. Nobody challenged that additive structure because that's what God made, right? God made the integers and everything else is the work of man. But we can really challenge this dogma. It's a dogma that we have this additive commutativity. And I, in 2016, challenged this. Maybe it was a midlife crisis. It was a little bit like a teenage rebellion. You want to kind of think, is there something maybe more fundamental? And indeed, I quantified this in a very precise way in Archive 2022. After a health scare, I was looking at things I have done, and I had a 40% chance of survival because I was in the hospital, and the doctor told me, the survival probability. And I thought, that's if I'm dying and I have something in my hard drive and it dies with me. What would be the most terrible thing? And I think it's this work from 2006. I think is kind of the most interesting thing I have done. And I was asking myself, if you have an algebraic structure like a group, which is also a metric structure, and you can ask yourself, if you forget about the algebraic structure, can you from the metric structure reconstruct the algebraic structure? And I call this a natural group. So it turns out that the integers are not natural, because on the integers you can also produce another group structure which still preserves the metric, the natural metric which you have, the translation invariant metric. And so the other group which you have is a non-abelian group, so it's not isomorphic, which is the infinite dihedral group. So this is exactly somehow more natural, because it's not just one generator A, right? A plus A plus A plus A, that's the Shannon picture. But there are two generators, both are reflections, and both have this Pauli principle thing. So it's like a creation operator and an annihilation operator. So you have this A and B, and A square and B square are both have this property that they satisfy this Pauli principle. So the elements are then just, kind of these strings, AB or ABA or BAB. And one of the things I really like about this, first of all, it's a natural thing. From that, you can actually build a metric space. I have just an asymmetric metric on the integers, so that this is the only group which is really possible on that structure. But it's also kind of, you have this Grothendieck completion is not so, artificial. It is very natural to think about A. And so the B, that's already there. That's the -1. The antiparticle is already there. Addition is the join with a twist. The twist is that you change sign. You change the particle nature if it's an odd number of particles. So in this case, when it's odd, you do that. So that produces a non-commutative addition. The multiplication you can keep, and algebraists call this a near ring. So in a ring you have the addition is commutative. In a near ring the addition can be non-commutative, and then the distributivity only works one-sided. So you have only a left distributivity or a right distributivity, and that's so it looks maybe a little bit artificial, but it's natural in the sense that if you give just a topology, that's the only thing you can do. It's also interesting that when you extend this, for example, you go to you put more structure on a number, like this geometric picture of a partition. You can think about this as kind of 3 particles. So you have one particle here, then you have a particle here, and you have a particle here. So this particle type has creation and annihilation operators, this has creation and annihilation operators, and so on. So they are independent, and the addition is the natural thing. You just throw the particles together, and if they have the same type, they behave like fermions, and if they are different types, then everything commutes. So, and that can be extended also to graphs, right? For graphs we have a nice ring structure. We have the addition, which is the join, for example, in the Sabidussi picture, or we have the and then the multiplication is the Sabidussi multiplication or the large multiplication, or then you take the disjoint union as your addition, and then you have the Shannon multiplication. So, and this is not a natural structure also in that sense, which I have written about in 2022, has to be enhanced. And what you actually make it a near ring. So that's what I wanted to say today.